So on page 29, we start page 16, and there's 3 parts of chapter 16, that we're going to do. First is, this chapter is about discrete variables, okay? So when I say that, then you're like, well, what the heck is discrete? So I need to first explain to you what is this concept of discrete. So here we go. So a discrete variable is one which takes on a countable number of distinct values, such as how many children you have. You know, 1 child, 2 child. It's not infinitely many small possibilities that I have to count. If the random variable can only be a finite number of values, then it is discrete. Okay? Examples would include number of children in a family, the Friday night attendance at a movie, the number of patients in a doctor's surgery, which is weird. I would think that's 1, but or 2 maybe. The number of defective light bulbs in a box of 10. So these are finite, countable amounts of items. Okay? And then you would say the probability of each thing. But continuous, we've seen continuous when we did our normal model stuff. Continuous is when you have probabilities of, and there's infinite possibilities, like, you know, your heights could be measured in small little increments. So small of increments, you know, you can have like 0.2225369 inches, you know, 6 feet, 0.22, whatever inches. So the amount of sugar could be little bitty small infinitesimal amounts of grams, you know, or milligrams or micrograms or whatever it is. So you can measure these small amounts. So that's considered continuous because it's infinitely many possibilities. So I want you to take a look at these 4 items and label each of these 4 situations as a discrete situation or a continuous situation, okay? So you can just put a D or a C on that, and so take a second and figure. Okay, so how about the number of desks in a classroom? Okay. Fuel efficiency in miles per gallon, distance a person throws a baseball, and the number of questions asked on the final exam. Okay. Now, this is interesting. I want you to think about this situation. What if I asked you the average number of desks per classroom? So that's not in a classroom, but the average number per classroom. What kind of numbers are those going to be? Yeah, those are going to be continuous. Because, you know, you could have, on average, in Aledo High School or whatever, then that's, you know, 12.35 on average, or whatever it is. Okay, so in that case, it turns into continuous. Okay, so interesting how that changes there. Now we're going to play a game, and to talk about our next goal. The next goal is to find out what the expected amount is. So on average, in the long run, what's expected to happen? Casinos deal a lot with this. Insurance companies and long-term probabilities play into this. What did we talk about in the past, right before Thanksgiving, that talked about how your probability in the long run is going to settle down to what that true theoretical probability is? What did we talk about on that? We did our flipping of the coins. What was that called? Anybody remember? If you do many trials, many trials, the cumulative probability, it will settle down to the true probability, the law of large numbers, you see. Okay, so that's the law of large numbers that we're counting on, that true probability will pan out in the end. Okay, and that's going to play into seeing what our expected value is. So we're going to play a game, and here's how it goes. I'm going to give you each Monopoly money, $5. Okay, and you can buy that. You can buy a stamp with it from me. Okay, so basically I'm giving everybody a free stamp. Well, then, but I'm going to give you a chance to gamble your $5 to see if you can get more stamps. Okay? So if you come up here, you pay me $5 to play, and then you can pick out of this well shuffled full deck of cards. And if you pick the Ace of Hearts, I'll give you $100 back. Okay, which is 20 stamps. I've had that happen. Last year was Andy Bright. He got 20 stamps. Okay. He was super pumped about that. So if you get any other ace, so one of the other 3 aces, then I'm going to give you $10 back. And if you get another one of the hearts that are in there, I'll give you your $5 back. Anything else, you lose and I keep your $5. Okay? So you're going to think about wanting to play that. Let me go ahead and pass out your $5 to you. I've heard people today tell me, oh, it's rigged, or I'm cheating and that's not really a full deck of cards, that kind of thing. So let's talk about what, on average, is expected for you to win or lose in the long run. Okay? First, let's talk about this, this game. Was this game a discrete or a continuous game? It's discrete because there were 1, 2, 3, 4 situations that you could win your money. 4 different amounts of values that you could get. Okay, so here we have it as discrete. But now let's go and make a table of these discrete events. So at the top of your next page, what was the largest amount that you could win? How could you win the largest amount? By getting an Ace of Hearts. Okay, Ace of Hearts. And so if you got the Ace of Hearts, how much money did you win? How much? Okay, you got back $100, but what did you first have to do? Okay, so you paid me $5 and I gave you $100 back. So ultimately, what profit did you make? $95, okay? And what's the probability of that happening? 1 out of 52. Okay? All right, what was next? Any other ace? Yeah, the other aces. What kind of money changed hands there? You paid me 5 and I would give you 10 back if you won. So ultimately you profited $5. How often does that happen? What's the probability? 3 other aces out of the 52 cards in the deck. All right. After that, how else could you win or get something back? Any other heart? And so you gave me $5, I gave you $5 back. So ultimately, what happened? You broke even. You didn't lose, so that's good. You broke even. And how often would that happen? What's the probability? There are 12 other hearts besides that Ace of Hearts. And so that's 12 out of 52. And I'm just going to leave those denominators as 52 so we can add these fractions together or easily and kind of see. Anything else, what happens? You lose $5. Now, we need to figure out how often that happened. That's the rest of the deck. What's the rest of the deck? What is it? Gotcha. Do you see this part here? That part accounts for 16 out of 52 parts of the deck. So therefore, 100% minus 16 out of 52 is 36 out of 52. So that's what you would always do if you had a part that is missing, guys. Sometimes that's the easiest way to find what's missing. Add up what you have in there and then subtract that from 1 to put what's missing. All right, very good. So now we're going to see what is expected that you win on average in the long run. And it comes from this formula. This formula, this E, stands for expected value. That's the same thing as the mean of this event. What happens on average in the long run? So let's examine this formula here. This symbol, capital sigma, means to do what? Sum. Okay, so we are going to sum up some products. The product of the little x value, that is an individual x times, what do you think that p with a little I is? The probability of that happening. So we would take the individual event times the probability of that event happening, and then when we would add to it the next one, and then add to it the next one, and so on. So in this case, that looks like this. So our expected payoff for you guys in the long run, what you will win on average, $95, 1/52 of the time, plus, what's next? $5, 3/52 of the time, plus $0, 12/52 of the time, minus $5, 36/52 of the time. And if you multiplied all that out, you would get negative $1.35. Negative. Ooh, what does that mean, negative? Yeah, you're losing money. On average, in the long run, every time you play this game, you're doing what? Losing $1.35. So let's interpret this result. Yeah. In the long run, a player loses $1.35 each time the game is played. On average. In the long run, because the law of large numbers says that in the long run, you will win $95 1/52 of a time. You will win $5 3 out of 52. These probabilities will happen in the long run per the law of large numbers. Okay, that's why law of large numbers is important. Casinos and insurance companies and anybody who uses the actuarial tables and these probabilities banks on literally the fact that in the long run, this is the amount of time that you will get $95. This is the likelihood of you to get $5 and so on. So a couple questions here. When you come up to me and you play, is it possible for you to lose $1.35? No. Well then, why is this $1.35? And how can we say that if that's not possible when you come up and play? What? It's an average. This $1.35, losing $1.35 is what happens on average every time you play. Meaning, say by the end of the day or by the end of the month or whenever, however long it was, on average, you lost $1.35 for every time you played. Okay? So if you're one of those people who gets ahead of the game and gets a $95 one, you better stop, because from there it's probably just going to be, the probability is more likely that you're going to be going down because you will end up at negative 135 per play. Okay, now a couple things. One is I want to show you where this is on the formula chart. I've kind of skated past formula chart stuff, so let me show you that real quick. This is the formula chart that you have in your packet, and what's over here on the left hand of the front, this left side is a whole bunch of big old formulas, and this is on the AP exam, the formula chart they give you, that we're pretty much not ever really going to use. There's only one of them that you probably need to find on there, and that is the slope. So let me show you that one. down here on the left. Do you remember the slope being the r times the standard deviation of y over standard deviation of x? Remember that? Correlation times the variation in y over variation of x, that's the slope. So it is there, FYI. But we will use this entire right-hand side of this entire right-hand column, and we're pretty much going to use most of it, or a lot of it, during this chapter. So let's get started. Take a look at this first one. Probability of A or B is probability of A plus the probability of B, but take away the part that got double counted. Haven't we already done that one? Yes, we saw that. That's the or, okay, and taking away the part that gets double counted. We've already seen that one. So check, we've done it. Second one, probability of A given B. You put in all those B's on the bottom, and you got the probability of A and B on the top. Done that? Yes. Check mark. That's why yesterday, while you took your quiz, I put it up here for you to see, because that is given to you. Anything you have available to you on the AP exam is always available to you in this class, okay? So here are the two formulas that we're going to learn today. We're going to learn what this expected one is. Actually, we just did, right? We summed up those individual x's times their individual probabilities. So we just did that one. Boom. Now we have to do this standard deviation of that expected amount, and that is this next formula that is quite a bit more involved. So let's take a look at it. So here it is. Let me move these guys down real quick. Okay, so this formula is the variance, not standard deviation. How do I get from the variance to the standard deviation? I heard it, whatever, square root it. The variance is the standard deviation squared. So once I get my answer, I'll square root it, and that'll be the standard deviation. So I want you to take a look at this. This, of course, is, again, summation. This is the individual x, that's your profit, minus, what does this mean? What is that right there? That's the negative $1.35 that we just got a minute ago. Okay? Quantity squared times the probability. So I'm going to start it, and then I'm going to let you finish it. So this standard deviation squared is, here's the first one, the $95 minus the mean, which is negative $1.35. So it's minus the negative $1.35, quantity squared, and then times the probability of that. What was the probability of the $95 one? 1 out of 52. Okay, there's the first one. Plus, okay, all four of them, yep. Here's the second one. $5 minus negative $1.35, quantity squared, times 3 over 52. Plus, okay, I want you to do the next two on your own. Let's see if you get them right. Okay, so there's the other ones, and I don't know exactly the number that you get whenever you do all that in your calculator, but I do know that when you take the square root of that number to get the standard deviation, the answer for the standard deviation is $13.80. Okay? In my mind, that's a lot of variation. I mean, you could be making $13.80 per play on average, down to losing a whole bunch more. I think that's what makes gambling so appealing, is this hope that you're going to be one of those way high situations, okay? Now, Do you want to do all that in your calculator by hand? I mean, do you want to do all that multiplying by hand? Oh my gosh, there's like so many possibilities for having a user error. So I'm going to show you how to let your calculator do it better. Possibilities, not possibility. Okay, so here we go. To your calculator. First, in your calculator, go and put in your calculator, go and put the table into your L1 and L2. Put the values you're going to profit in list 1 and the probability fractions in list 2. Okay, stat edit. What you profit in list 1 and your probabilities in list 2. Okay? Now, after you have done that, then you're going to do stat over to calc, stat over to calc, one variable stats. Stat over to calc, one variable stats. Now, if your stat wizard is on, then you get this menu right here. The list is list 1. The frequency is those probabilities. Probabilities are how often you expect them to happen. So that's in your list 2. So for these, if you don't put the frequency as L2, then all it will be doing is giving you an average of the numbers in list 1. Okay, and then you calculate. If you do not have Stat Wizard on, then here's what you do. You've got one variable stats, and then you've got list 1, comma, list 2. List 1, comma, list 2. So it's list 1 with list 2's frequency. The comma, I think, is above the 7 or something. I don't know. Okay? So once that happens, these are the numbers that you get, that your calculator gives you. Okay? Well, what's X bar? Yep, X bar is the mean of X, and Y bar is the mean of Y. So X bar, dun, 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 negative $1.35. It rounds to. See, so voila, you didn't even have to do all of that other stuff up there in the formula. And do you see the standard deviation here? Right here, standard deviation is 13.80. So thank goodness that that is there, and you do not have to do all of this formula stuff in your calculator. Oh my gosh, it's a nightmare. I used to have my students do that because I didn't know that little calculator trick. Oh my gosh. The grading was horrendous because, you know, if you make a little calculation error, I made you show the work. Well, you showed the work, you just calculated it wrong. But then I had to follow your wrong answer through the whole rest of the quiz to see if you did all the other processes right, but with the wrong answer. Oh my gosh. It was so annoying. So I'm glad to have this calculator trick. So there you go. All right, questions there. Okay, then we got one last thing that I want to discuss, and it is this little section down here. And it is about draw a normal model to represent the expected profits. Okay? Hey, here's my question. The amount that you lose or make on average, what kind of value is that? Discrete or continuous? Yeah, because you made $1.35, or actually remember it was negative 1.346153. This is continuous type numbers here. So once we turned them into an average, it's now continuous. So watch what's happening. Here is our continuous information, and I've got a average of negative 1.35. Let's put our little standard deviations in there and see what all of these numbers look like. I'm going to go up 13.8 and I get 12 point, I think it was 45, and then 26.25, and then 40.05. There's your positives going up. Going down is negative 15.15, negative 28.95, and I actually don't know what that other one is down there. Okay, here's my question. What percent of the time do you lose money? It's more than 50. How do you know it's more than 50? Aha, because the mean's negative. So I need to identify where the break-even point is. What's the break-even point? A 0. Okay, so that's somewhere right in here. Okay, so somewhere right in here is a value, an x value of 0. So ideas on how I can figure out the percent of time that you lose money. Oh, that's for one, that's the probability for one thing, not what happens on average. Okay, yeah. What's the percent of time that you average a losing amount? What can I do to find that shaded area? Yeah, norm CDF, but what do I have to do first? Z-score, what's my X value? 0, because that's where I break even. X minus the mean over the standard deviation. And that Z-score is 0.0978. So I'm now going to norm CDF from what to what? No, the lower part of that. Negative 99 to 0.0978, and that is about 54% of the time. So about 54% of the time, when you go home, you have averaged a losing number on every single one that you did all day long. That's a lot. Okay? So 54% of the time, you're going to be losing, you average losing every single time. So I had a regular deck of cards. Did I cheat? Did I do cheating? But as a casino, am I going to come out ahead of the game? Do I want to get as many people as possible to come into the casino and play this game? Heck yeah. Because the more people that come, every single time somebody plays, I'm going to make $1.35 on average every single time in the long run. That's how casinos get you. It will happen. The law of large numbers says so. Okay, so we're done with that. Now, I want to go over to page 33. So we're kind of done with the learning part. Turn over to page 33. Ooh, do we only have 3 minutes left? Dang it. Shooty Rooney. Okay, so let me help you with number 2. Okay, you're going to do problems 1, 2, and 3, and that's it. So don't go past 4. Okay, you're going to do problems 1, 2, and 3. Actually, will you go ahead? I'm going to have you write this down on number 3 because I don't have time to go over it with you. Here's some hints. Okay, you ready? This is actually the way, a simplistic way of how insurance works. You pay $100, and you could either have a major injury, a minor injury, or no injury. So that's what that says across the top. Major injury, minor injury, or no injury. For no injury, the insurance company has made $100 because that's you paying them $100. But look what happens on the major injury. You give them $100, but they pay you back $10,000 if you get a major injury. So in essence, the insurance company has lost $9,900 for every major injury. And that occurs 1 out of 2,000 clients or customers. For every 1 out of 2,000 people, they're out $9,900. Okay? And then the probability of a minor injury, it says, was right here. How could you find what's missing there? The missing probability. Yeah, subtract the other two probabilities. Okay, and you can read up there and get the minor yourself. Let's go back to the number 2. Let me help you make this one. Create a probability model for the number of children that will have couples. Here's the little rules that they're going to go by. A couple plans to have children until they get a girl, but they will not have more than 3 children, even if all are boys. So what could happen straight out of the bat? They could get a girl, and then they are done. How often does that happen? That's a 50% chance that their first child will be a girl. They will be finished. Then, how could they have 2 children? They first get a boy, and then they get a girl, and then they stop. What's the probability of getting a boy and then getting a girl? 1/4. How else could this play out? Boy, boy, girl. That's a half times a half times a half, which is 1/8. But there's another way that they could have 3 children. Boy, 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 because they're going to stop regardless. So that's a half, half, half. That's another 1/8. Okay? So let's fill out this chart. What is the probability that they will finish with 1 child? That's that right there, 1/2. What's the probability that they will finish this scenario with 2 children? 1/4. And then what's left would be the 3 children, which is the 1/8 plus 1/8. Okay, so I need you to finish those problems there Sunday night or whenever it is that you do your homework. Oh, pooh! Oh my gosh, I didn't stamp you. Okay, hold on.